Hello students, in this video we'll begin our discussion of continuity of functions of a single variable. Let's suppose we have a function f which maps e into r and a point c that is in e, and c is a point in e. We say that f is continuous at this point c if for every epsilon greater than 0 there is a delta greater than 0 such that what? Such that x minus c less than delta implies that f of x minus f of c less than epsilon. Notice that this is very similar to our definition of functional limit existing. If we recall what the functional limit definition was, the functional limit definition was this. We said that f of x approaches L as x approaches c if f of x minus L is less than epsilon, if 0 less than x minus c less than delta, right? That was our definition of functional limit. In the definition of functional limit, x was not allowed to be equal to c. Over here, we're specifying that c has to be in the set E. It has to be in the domain of f, because the limit condition over here is that we want to measure f's distance, f of x's distance, against f of c. So there's a fundamental difference over here. The difference is that the c has to be not a limit point. Well, c will be actually in the set E, not necessarily just a limit point like it is for functional limits. All right, good. So let's see an example of showing something's continuous. Let's start with a prototypical example. So the prototypical example will be our class of linear functions. If I look at f of x is equal to mx plus b, where m and b are just constants, linear functions should be continuous. So let's see. And so I'll skip the scrap work because of a good sense that we know that this m over here is going to represent what's the sort of the rate of growth. So that's going to have to be the rate of growth of x relative to the f of x rate of growth. So what we're going to do is we're going to let epsilon be greater than 0 and pick delta to be epsilon over m. If we suppose that x minus c is less than delta. Now I'm letting c be an arbitrary number over here, so c is just an arbitrary point because the domain of f is everything. So f over here is going to map r to r, so we can pick any c. So any c in r will work for this function. Okay, good. Now what can we say? Then, well, I'm going to look at f of x minus f of c and see what we're going to get. This is going to be mx plus b, then minus mc plus b. Of course, the b's are going to cancel out over here, and we're just going to have a factor of m. And we should make, of course, m could be negative over here, so let's put an absolute value on m to correct that issue. So I'm going to have an absolute value of m that comes out. Then I'm going to have an x minus what? X minus c, which is absolute value of m times what? It's going to be strictly less than, so strictly less than delta, because x minus c is strictly less than delta. And now delta is equal to epsilon over m. So this is absolute value of m times epsilon over absolute value of m, and that simplifies to epsilon. So we've just shown that if x minus c is less than delta, f of x minus f of c is less than epsilon. So this shows that these linear functions are continuous. So hence linear functions are continuous. In fact, something actually is better. We're going to see this later, they're actually uniformly continuous because it didn't matter what point I picked. I had the same sort of modulus of continuity, so they're uniformly continuous. Okay, let's do one more example that's sort of quick. Let's show f of x, which is sine of x, is continuous. Let's do a simple point. Remember, continuity is a local point. It's relative to a fixed point over here. Let's continuous at x equals 0, okay? So I'm going to skip the scrap work. I'm going to let epsilon be greater than 0 and pick delta to be epsilon. Suppose that x minus 0 is less than delta, which is equivalent to what? Equivalent to just x less than delta. Then sine of x minus sine of 0 is just sine of x, an absolute value. And sine of x is no larger than x because it's just the sine of an angle is no more than the arc length of the corresponding angle. So that's less than or equal to x, which is less than delta, and that was equal to epsilon. So we've shown that if x minus 0 is less than delta, then sine of x minus sine of 0 is less than epsilon. That proves that sine of x is continuous at x equals 0. Thank you very much.